again, guys, thanks for coming back for more. This little clip extends, of course, the last ideas of half reactions and redox equations to that of producing an electrochemical cell, like a battery type device. And if we can harness that transfer of electrons between one reaction and another, we can get what we call the standard voltage, the standard potential the difference between the reduction, and calculate how good of a battery, how much voltage a particular battery can deliver. So here's a little diagram I clipped off the internet. I just labeled it standard silver electrochemical cell. I called it the silver because I put a piece of silver over here into some 1 molar silver water. And over here I had the standard reference electrode called the standard hydrogen reference electrode, SHE, capital letters. This is a really weird setup if you think about it, because who would really think of putting hydrogen gas through or in contact with this 1 molar acid water and put a little platinum unreactive platinum electrode at the bottom and hook that up to an external wire. Honestly, I'll bet Volta and Galvani had some ideas about this, but we all reference it relative to the hydrogen. So I can replace this with zinc, with iron, with copper, with cobalt, with chromium, with whatever you want. Or you could even replace this with another gaseous, gas phase, aqueous phase contact platinum wire, and compare that gas to this gas. In any case, in this particular example with the silver, it looks like the electrons are encouraged to flow from here over to here. Let's see, why would that be? If you guys got that announcement that asked you to print that table of reduction potentials, that would be very handy to have. It looks like... I didn't finish my sentence over here. Oh well. Did I? Oh, I put it up here. Yeah, let me come back up there in a second. Sorry, I'm so all over the place today. Here, according to this diagram, in any case, the silver, the electrons travel this way. The negative is attracted to the positive of the silver ion in aqueous solution. And I guess we're having a reduction of the silver ion to silver, pure silver. So this electrode would actually, let's see, reduction occurs at the cathode, and this electrode would be getting heavier and heavier as the silver ion grows out of the water, gaining electrons onto this. Electrons come down, are attracted to those silver ions in the water, and they meet up right here and form solid silver crystals on the surface of that electrode. That's the reduction. And I looked this up in a table somewhere. This one over here, by definition, this H2 at 1 atmosphere and this hydrogen ion at 1 molar in contact with each other, that's, we're going to call that, it sounds kind of weird to make up your own definition, but they do, and we call that the zero potential. So if I write the equation this way, or if I turn it backwards, in the case of very active metals, we'll actually give up their electrons to the hydrogen ion to make hydrogen gas. Still a zero. Alright, another way to write this mess is with what we call cell notation. As it's written, usually we put the oxidation half reaction on the left and the reduction half reaction on the right, and the double lines mean a salt bridge in the middle. And standard conditions are 1 molar and 1 atmosphere pressure, and usually room temperature-ish. As this battery has, oh no, wait a second, that's not right. Yeah, this is the reduction. So usually I put the oxidation over here. So I have the platinum metal in contact with the hydrogen gas, which is also in contact with the acid water. And then I have the silver, which is actually over here on my picture, in contact with the 1 molar silver water. So that's shorthand notation for this diagram or something like it. Alright, let's try a few. So what if I wanted to make a battery with these two half reactions? The story goes like this. Whichever equation whichever half reaction I hope to use that is more positive, i.e. less negative, will be the reaction that happens as a reduction in the order given. So if I hope to make a battery from fluorine gas and gold, my bad, fluorine gas and gold, I look up the two half reactions. This one's more positive. Why would you want to make a battery from gold? Well, why would you want to make a battery from fluorine gas? It's just a nasty gas, but, hypothetically speaking. The more positive one is the one that happens, and the one that's less positive or more negative ends up getting flipped backwards. And if I flip this backwards, guess what happens to the positive 1.5 volts? Changes to negative 1.5 volts. So this might contradict a little bit of the way your text might tell you to do it, but I don't read the text much. I do it the way I do it, and whatever works, because I know this always works. So here's my fluorine reaction. I left it as it was written. I flipped this gold 3 plus idea backwards. So I'd be basically replacing up in the picture, I'd be replacing this with fluorine gas and a platinum wire and some fluoride water. And over here I'd be placing this with gold and gold plus 3 plus. I think it was 3 plus water. It's a crazy idea, but it would work. What would be the voltage of such a battery? Well, if I was making sure that the electrons matched up, I'd want to, of course, take this times 3 to make that 6 electrons match up with 2 times 3 is 6 electrons here. But the real question right now is, how does this combine with this? Well, the answer is you just add them up. So what we call by the way, so I went ahead and took it all times 3, take it all times 2, make the electrons cancel. And the whole point, the new point here, is that the cell would have a potential of this one plus this one, which is basically 2.87 minus or plus a negative 1.5. And yes, I would measure with a voltmeter as in the picture, the external to the two half cells. I would measure on that voltmeter 1.37-ish volts. So yes, it would be an okay battery. And this would perhaps also be an okay battery. Let's figure it out. Again, I said the more positive or the less negative is the one that happens in the order given. You can say the same thing for switch them all backwards and call them oxidation half potentials, and the same story is true. But whatever's more positive, reduction. This is more positive, although it is negative. I'll just call it less negative than this one. So I'm going to end up flipping this one backwards, so I can have a cobalt 2 plus cobalt, manganese 2 plus cell. So I believe I flipped that one backwards as an oxidation, called it oxidation, standard conditions, 1 molar solutions, room temperature, etc. So I looked these up on tables, except this one flipped from negative to a positive 1.18. And indeed, my battery under normal conditions, the cobalt manganese battery, would work pretty well. Positive 0.9 volts. Oh yeah, so I said this is my full reaction, transferring 2 electrons each. It's spontaneous because that's positive. Here's the shorthand notation for that. Oxidation on the left and reduction usually goes on the right. But remember, if I flip that equation backwards, if I flip this backwards, so it looks like this, then my positive 0.9 volts goes to negative 0.9 volts, and voila, my battery is not going to work. So if I really wanted this to go, I would actually need a battery to push it, to take the electrons off of cobalt and put them onto the manganese to do this. Interesting, y'all. Let's try another one. What if I wanted to make a battery from bromine and silver? Can you make a voltaic cell with bromine and silver? So I take the bromine half reaction, the silver half reaction. I saw that's more positive than that. So this one's going to happen in the way order given. It's going to gain electrons from the silver. So I'm going to flip that silver reaction backwards. Or I could say, take the silver, put it here. Take the silver 2 plus, put it here. 2 silvers, 2 electrons. And I ended up switching the silver reaction backwards, so it changed from a positive 0.8 to a negative 0.8. And the answer is yeah, it still works as a battery, still functions. The voltage is kind of low, but I called it a good battery as in the sense that it's positive and not negative. We haven't seen a negative cell potentially yet, but we should. What about the aluminum beryllium aluminum, aluminum 3 plus, beryllium 2 plus, beryllium battery. What kind of cell potential will I get out of that? Well, I pull out the half reactions, aluminum goes there, aluminum 3 plus, lose electrons, beryllium 2 plus, beryllium, there's a 3 in front, there's a 3 in front, I figured it would be 6 electrons, and yeah, those would add back together to cancel the electrons. So I got this 1.66 from this reduction half reaction, although remember that if I multiply this equation by a number, it does not change the reduction potential. This is all referenced just to a different element, hydrogen. So it's just the particulars of the elements right now that give us these standard potential numbers. And this one was flipped backwards from the beryllium gaining 2 plus gaining electrons. So I took the negative 1.7 to a positive 1.7. Then I rearranged them back together just so I could see how the 6 electrons cancel, and my voltage comes out slightly negative. I on purpose chose it so that it would, and also chose it so that the aluminum and beryllium are so close to each other on the table of reduction potentials that it's not a very good battery in the first place. Well, it's not a negative battery for one thing, and it's not very far away from zero in the other place, second place. But if I choose these two half reactions further apart on the list of reduction potentials, then I will get a more positive or more negative battery. Depends how you look at it. Alright, that's it. Thanks, guys. See you in class.